So here we are. Let's continue with Chapter 7, Production Technology. Last time we talked about short-run production technology, and today we want to talk about production technology in the long run. The distinction being, of course, that in the short run, at least one production input is fixed and one production input is variable, so that we can only change the level of output by making changes in our variable input, but not the fixed input. And in the long run, then, our production will be such that all inputs are variable. So that was our distinction between the short run and the long run, is a period of time that it takes in order to be able to change all production inputs. Now I want to go back, because last time I made an algebraic mistake and I don't like that. So let me go back to what I was doing last time, and we will, let me correct my mistake here. So what I had was a short run production function, which you may recall was Q is equal to 4L plus L squared minus 0.05 L cubed. And we said that the average product of labor then was, Q over L, or 4 plus L minus 0.05 L squared. And what I did was I solved for the value of L at which average product is at its maximum by setting average product equal to marginal product. And when I did that, then I reached the conclusion that average product reaches its maximum with 10 units of labor inputs. And then I said, that's not what I'm looking for necessarily. I may be looking for what the max average product is, in which case I need to evaluate average product of labor when L equals 10. And so what I said here was average product of labor then equals 4 plus L, and this should have been a minus 0.05, not a plus 0.05. So I'm going to get rid of all of this, and I'm going to make this a minus 0.05 times 10 squared. So I've got 14 minus 5. The correct answer there should be average product of labor is 9, not, excuse me, not 19. All right, so that done. Let me now get back to thinking about what long-run production technology would look like. So I'm going to move now to the PowerPoint and continue with that. So here we are, we're back in a world of a firm producing some output, some good, service, with two inputs, capital and labor. And in this scenario here, we define a production function then that describes this production technology, which is to say, for what quantities of labor and capital inputs, the highest attainable level of output that can be gotten with this particular technology. So, we had before the notion that if capital is fixed, if it takes some amount of time to vary your capital inputs, whether it be plant, equipment, whatever, that we're in a short run situation. And in this two input world, only labor is variable. Now we want to move to a long run. And, I was saying last time, the long run we might think of as sort of a planning horizon, when you can pick whatever capacity you want, whatever capital amount you want, and then, move to a different short run in essence. But what we're supposing here is that there is some degree of substitution between our inputs, so that we can substitute one input for the other while holding output constant. That is to say, that I can say add 2 units of labor to my production process and reduce my capital inputs by some quantity without causing my output to fall. So there is some substitution, albeit perhaps imperfect, between capital and labor, or as we want to state it, labor for capital. Now, if you look at this tabular form of a production function for a firm producing garden benches, and this is production technology, and for a firm who this is a fixed technology for a firm who's using both labor and capital. And as you can see, there's some substitution. So if we were to focus just on producing 140 garden benches per week, we could do so with 2 workers and 2,500 square feet of garage space. So 2 workers and 2,500 square feet of garage space. So this garage space is our capital, it's our building. This is our labor here along the horizontal, with the rows here, and the columns are different capital inputs. Now, we could also give up 1,000 square feet of garage space and add an additional assembly line worker. So we've substituted assembly line workers for garage space, and we've held output constant. So there's some substitution allowable there. And we could also substitute an additional 2 additional units of labor for 500 square feet of garage space. So we could also produce 140 benches using 5 workers and 1,000 square feet of garage space. Now, this is what, we've done before, largely speaking, when we spoke in terms of utility. In this context, now we're speaking in terms of output or production. So what we're describing here when we say, well, what are all the different input combinations that will produce 140 units of output? Well, that is what then we call an isoquant. Iso for same, quant for quantity. And an isoquant is a curve that shows efficient combinations of labor and capital that can produce a given or a single iso level of output quantity. And the equation for an isoquant then is going to be the relationship between L and K that are both variable that produce a given fixed Q bar quantity of output. So, as I say, we usually write in standard algebraic form that, Y, where is our, variable on the vertical axis or the dependent variable, and where X is then the variable on the horizontal axis or the dependent or the independent variable, and Q we hold constant at Q bar. And so we have a relationship then that is a curve or an isoquant that illustrates all of those capital and labor combinations that produce exactly Q bar. Now, this is from your authors, the productive input principle. Increasing the amounts of all inputs strictly increases the amount of output the firm can produce. So if we increase both capital and labor, then we would necessarily view an increase in output. Now, this is different, as I say, from assuming that marginal products of all inputs are always positive. Analogous, more is better. Now note that we now have not only a marginal product of labor, but in this long run scenario with variable capital, we also have a marginal product of capital. So I now think of marginal product of labor being that change in output attributable to a small increase in labor, holding capital constant. But I also have a marginal product of capital, which is the increase in output gotten from a small incremental increase in capital inputs, holding labor constant. So, we say that this always has to be positive. Well, we would never use either capital or labor to a point where its marginal product was negative, because we could always get, if its marginal product was negative, we could always get more output using less of the input. So clearly it wouldn't be an efficient output relationship with our inputs if that was the case. But if isoquants always slope downward, then marginal products must always be positive. Now think about why that must be. If both of my inputs have a positive marginal product, then if I increase the amount of one input in my production process, all else equal, that's going to make output go up. So the only way I could stay on the isoquant, which is to say a constant quantity, would be to reduce the other input just enough that it offset the change in output from the other input, right? So, if I add a little bit more labor and output goes up by 3 units, then I would have to take away just enough capital to cause output to fall by 3 units in order to stay on the same isoquant, because the value of Q has to stay constant moving along that isoquant. So whenever I add one input, I have to take away the other input under the assumption that their marginal products are positive. So that tells me that an isoquant is going to be a downward sloping curve. And going back to that tabular production function, here are 3 input combinations that were in that table. That was 2,500 square feet of garage space and 2 assembly workers, or trade away 1,000 square feet in exchange for 1 assembly worker. So as we substitute assembly workers for garage space, note that the trade-off has to be just that there is no change in Q. All right. So as we substitute, and you can see where we're going here with this, we're going to get another, rate of substitution here. As I give up, 1,000 square feet of garage space in exchange for 1 worker, output has stayed the same. And here I give up another 500 square feet of garage space in exchange for 2 workers. So we're getting essentially toward, again, a substitution, a marginal substitution measure. So the isoquant itself identifies all input combinations that produce a given level of output. So this is the isoquant associated with Q equals 140. This is the isoquant associated with Q equals 150. And notice if we use more of both inputs, we necessarily move to a higher level of output or to a higher isoquant. And we have a whole family of isoquants which would correspond to all possible levels of output. So I end up with an isoquant map that looks just like an indifference map, only this is representing production technology in terms of the inputs required to efficiently produce all levels of output and the choices of different input combinations to produce every level of output. And I end up with this isoquant map consisting of downward sloping isoquants associated each with its own specific level of output. So, what are the properties of isoquants? Well, it's just, again, like if we increase both inputs simultaneously, then our output has to increase. So that means that the further we go to the northeast or away from the origin, the higher is the associated level of output. Isoquants cannot cross. They always have to slope downward as long as marginal products are positive. And as I said, if ever it was true that a marginal product of an input was not positive, then we would consider its use uneconomic at that quantity. So we would reduce its use until its marginal product was again positive at a minimum. So these properties of isoquants, they're thin. They can't be thick because in this case, again, we would violate that input principle that if we increase both inputs by some positive amount, output would stay the same. So B and A couldn't possibly be on the same isoquant because A would have to imply greater output than B. So isoquants have to be thin. They're 1 point thin. Isoquants cannot slope upward again, and we'll talk about this in just a minute, but the slope of the isoquant is indeed the ratio of marginal products of these two inputs. So the only way an isoquant could slope upward is if, note, going from B to A implies that we're, adding more labor and more capital. The only way output could stay the same when we add both labor and capital would be if the marginal product of one of the two inputs was negative. So that by adding more of that input, that would cause output to fall. So we have to add more of the other input whose marginal product is positive in order to keep output constant or move along the isoquant. So again, if ever an isoquant were to slope upward, suggesting a negative marginal product of an input, we would consider that to be an uneconomic region, and therefore we would disregard those input combinations as an economic possibility. And so, an isoquant is this boundary between input combinations that produce more. So, in the same way, it suggests a trade-off. We know that moving to the northeast from any point must necessarily imply more of both inputs, so output would have to rise. We know that moving to the southwest would imply less of both inputs, so output must necessarily fall. But how about these zones here, these regions here, toward the northwest and the southeast? Now we're talking about trading more of one input. As I move along the isoquant in this direction toward Q equals 100, I'm talking about adding labor and taking away capital. And I'm doing so in quantities and amounts of each, such that their contribution to output exactly offsets one another. So there's no change in output. And lastly, of course, these isoquants can't cross. Again, in this particular case, I know that C has to represent more output than B, again, because it has both more capital and more labor at C. So if C and A had the same amount of output, they're on the same isoquant, and A and B were on the same isoquant, but C is greater than B, that would be a contradiction. It can't be. So C cannot be equal to B. Therefore, if B is equal to A and A is equal to C, we've violated our transitivity. So let me move through what all we have here. All right, so in higher level isoquants, as we said, as we go to the northeast, are associated with higher levels of output. Now, let's go back to this. This is again, I kept saying that the marginal rate of substitution in terms of our model of consumer choice was critical for us for our model to work. We're now going to generate a construction that's very similar to marginal rate of substitution. We're going to call this the marginal rate of technical substitution. And that is to say, the number of extra units of one input needed to replace one unit of another input such that the amount of output remains constant. Now, we're going to talk about this in terms of capital and labor. So when I look at the slope of an isoquant at a point, that is going to suggest to me the slope of that isoquant. How many units of capital we could forego in exchange for one additional unit of labor, keeping output constant. Let me say that again. The marginal rate of technical substitution in our context here tells me how many units of capital at most, the amount of capital that we can eliminate in exchange for an additional unit of labor. So the slope of the isoquant is delta K over delta L, rise over run. So my delta K is a change in capital, units of capital, for, and keep it simple, for a 1 unit increase in labor. So if I were to look at my isoquant here, and we were to consider moving from point A to point B, this is sort of a lumpy way of thinking about it. It says that I can give up 50 units of capital. From B to A, I go from 1,050 units of capital to 1,000, so I've traded away 50 units of capital. In exchange, I add 50 units of labor, and output, since we're on the same isoquant, is unchanged. So the slope of this secant line here is -1. Now, as this is drawn, you're going from A to B, they're saying, okay, we're going to take away 50 units of labor in exchange for 50 units of capital. Output stays the same. The slope of that secant line then is -1. More specifically, however, we think at point A, the slope of the isoquant at the point A is the same as the slope of a tangent line to the isoquant at that point. And this is what we think of then, the negative of the slope, because we think of MRTS, marginal rate of technical substitution, substituting labor for capital. We think of that as a positive number, therefore the MRTS is the negative of the slope of the isoquant at any given point. And it has that interpretation for me. If the slope of the isoquant at this point was -1/2, all right, so the slope of this line here, tangent to the isoquant at point A, was -1/2. That says that we can substitute labor for capital at a rate of 1/2 capitals per unit of labor. Remember, it's delta K over delta L. And so we can substitute the rate of 1/2 capitals per unit of labor, holding output constant. So the MRTS, the rate at which a firm must replace units of X with units of Y to keep output unchanged, or the rate at which the firm must replace units of Y with units of X to keep output unchanged. Okay. Delta K over delta L. So note now, if I look at this, how the marginal rate of technical substitution varies along an isoquant. Again, I draw this isoquant, which is now convex toward the origin. Capital on the vertical axis, labor on the horizontal axis. We're looking at an isoquant associated level of output of 10 units. Now, as we move along this isoquant, what you can see is at first, when we have a lot of capital and not a lot of labor, we can substitute we can give up a relatively large amount of capital for 1 unit of labor. So in this case, we're substituting labor for capital at 6 capitals per labor as we go from A to B. Now, as I use less capital and more labor, here we are going from B to C. I'm using more labor at C than I was at B, and I'm also using 3 units less capital at C than I was at B. But the rate of trade-off here was when I had a lot of capital and less labor, I could give up 6 capitals per unit of labor. But now when I move from B to C, I have, starting at B, less capital. And so now as I add a unit of labor, I only have to give up 3 capitals to keep output unchanged. And we keep this game up here, we keep moving down the isoquant, you can see that this marginal rate of technical substitution is decreasing. The amount of capital I give up per unit of labor decreases, keeping output constant. So, you know, what are we really looking at here? We're looking at moving down this isoquant, less capital, more labor. So what that means is, as we have less and less capital and more labor, labor has less capital to work with. And so the marginal product, as you would imagine, as we take away capital from our labor inputs and add more labor, the marginal product of labor is going to be falling. It's consistent with our law of decreasing marginal product of labor, but we're not only holding capital constant and adding more labor, we're actually taking away capital and adding more labor. So we have a decreasing marginal product of labor, but conversely, as you would imagine, as we put more and more labor to work on our capital, the marginal product of our capital is going to be rising. So here, marginal product of labor is high, not a lot of labor on all that capital, and the marginal product of capital is low. So we can really trade at a favorable rate. For 1 unit of labor, we can give up 6 units of capital just because the marginal product of capital is low, marginal product of labor is high. So it takes 6 capitals to replace a unit of labor. But as labor gets less capital and we get more labor, then the marginal product of labor is going to fall. The marginal product of capital is going to rise. So now a unit of labor can only replace 3 units of capital, and so on, 2 units of capital, 1. So let's think about this. The marginal product of labor is, of course, change in Q over change in L, all else equal. And the marginal product of capital is analogously delta Q over delta K, all else equal. So, as I say, these are just first partial derivative in this case, of the production function with respect to the 2 inputs. So note, if we were to arrange these expressions, we get, delta Q is equal to the product, marginal product of labor times labor, and delta Q is also going to be equal to, on the capital side of the equation, the marginal product of capital times the change in capital. Now, let me go back to my whiteboard here, and so let's think about this. This is a real similar construction to how we came up with the marginal rate of substitution. What we have here is we have the marginal product of labor is equal to delta Q over delta L. So what that tells me is then delta Q will be equal, just bring this up, will be equal to the marginal product of labor times delta L, all else equal. So this says if marginal product of labor is 2, and I add 2 units of labor, I would expect to get about 4 additional units of output by virtue of, each unit of labor produces 2 units. I add 2 units, I get that. I get that total of 4. Now I also have the marginal product of capital is going to be now defined as delta Q over delta L, which tells me then, doing the same rearrangement, that all else equal, delta Q will be equal to the marginal product of capital times the change in capital units. This needs to be a K there. All right. So that if the marginal product of capital was, say, 6, and I added 1 unit of capital, I would expect that unit of capital to get me 6 additional units of output. Now, notice if I put these 2 together. Suppose, I've got marginal product for labor is 2. Suppose I add 2 units. What's going on here? All right. So, what I'm saying here is that suppose delta L is equal to 2, marginal product of labor is equal to 2. Suppose delta K is equal to 1 and marginal product of capital is equal to 6. Then, when I move along an isoquant, I'm increasing L as I move down the isoquant and decreasing K. But if I wanted to know, I suppose we change quantities of K and L at the same time, what's going to be the simultaneous effect on output? Well, delta Q would be the sum of these two effects approximately. So it would be, well, from my from my labor side of things, I have a marginal product of 2 times I'm increasing my labor inputs by 2. So that tends to make my output go up by 4. And at the same time, my marginal product of capital is equal to 6. And I'm increasing my capital inputs by 1, that tells me that I would have an approximate change of 10 units of output when I change both at the same time. But moving along my isoquant, suppose I make delta K equal to -1. So now I'm thinking about increasing labor and decreasing my capital inputs starting at the same point. This would be approximately equal to, again, marginal product of labor of 2 times plus 2 labor inputs. Now in this case, I'm going to add my capital change. Oh, I need to make this a -1. Why do I keep doing this? So, all right, so I'm going to reduce capital by -1. So I would have a minus marginal product of capital, we said is 6. This should be a plus, -1. Right, so this is going to be 4 minus 6 equals -2. So in this scenario, if I added 2 labors and took away 1 capital, I would expect the net effect to be -2. Now, let me think about this more generally. So I've got delta Q is going to be the sum, approximately, of these 2 effects taking place simultaneously. The marginal product of labor times whatever change in L, plus the marginal product of capital times whatever change in capital. But if I'm moving along the isoquant, that tells me that delta Q has to be 0. So I end up with marginal product of labor times delta L is equal to minus marginal product of capital times delta K. And we're saying the slope of the isoquant, delta K over delta L, is the negative of the MRTS. So what this tells me is then that minus delta K over delta L is equal to the marginal product of labor over the marginal product of capital. And this is then the marginal rate of technical substitution of labor for capital. So the MRTS of labor for capital is the ratio. The ratio, marginal product for labor over marginal product for capital. Now note, in my world up here, I said the marginal product for labor was what? Was 2, and the marginal product of capital is 6. So if marginal product of labor is 2, the marginal product of capital is 6, what that tells me is I get 3 times as much output from 1 additional unit of capital as I get from labor. So I get 3 times as much output from 1 unit of capital as I do from 1 unit of labor. So clearly, it would take 3 units of labor to replace that 1 unit of capital. So the MRTS would be equal to 2 over 6, which is 1/3. And that tells me then that only 1/3 unit of capital is necessary to replace a unit of labor, right? So if capital is 3 times as efficient per unit at the margin than labor, then it would only take 1/3 of a unit of capital to replace a unit of labor. So let me go back to my other screen here. So what I just did, let me redo another example here. If the marginal product for labor is 4 and we hired 2 units of labor, then change in output from just the labor change is going to be approximately 8. So, since along the isoquant, delta Q equals 0, so we would have the marginal product of labor times change in labor, which I just did, plus the marginal product of capital times the change in capital has to equal 0 along the isoquant. So what that means is since both marginal products are positive, either delta L has to be negative or delta K. If delta L is positive, delta K has to be negative. If delta L is negative, delta K would have to be positive. But so this is the separate effects of changes in both labor and capital. So it's an approximation. But what we get to here then is the ratio of the marginal product of labor is equal to the negative of delta K over delta L, which is the negative of the slope of the isoquant at a point, and that's the MRTS. So A, B, C, as you can see, the slope of the isoquant is diminishing, but what's happening here, that means that the ratio M, the marginal product of labor over the marginal product of capital, is decreasing. So as I move down this isoquant, less capital, more labor. Think about this as saying more labor, less capital. So the labor has less capital to work with, so the marginal product of labor is going to be decreasing. As I move down this isoquant, we get more labor with less capital to work with. But more labor on our capital implies that the marginal product of capital is increasing. So the numerator in this expression is decreasing. The marginal product of capital is increasing. So if the numerator is decreasing, the denominator is increasing, the ratio is decreasing. So, if we think about, kind of special cases here, this again is very analogous to what we already did. If the functions of 2 inputs are identical so that a firm can exchange one for another at a fixed rate. Right, so this would be the case if their marginal products were positive and constant, they would trade at a constant rate. And as you can see here, this says that the marginal rate of technical substitution is equal to 1/2. So that says 1/2 of a college educated worker will substitute for a high school educated worker. So my wife. So if the functions of 2 input are identical, and I don't really like that expression for it, if the marginal products of 2 inputs are constant, let us say, then we would observe that the MRTS is constant. And since the slope of the isoquant is constant, that means that it is linear, All right, so 1/2 of a college educated worker substitutes for 40 units of a high school worker. Perfect complements, same thing like we did before. We'll go over some of these when we review on Friday, on the review class, the next class. Perfect complements, these are fixed proportions. So drivers and cars, shovels and workers, whatever. So in this case, it takes one driver, one car. You can have all the drivers you want, but you can't deliver more goods to people's houses or pizzas or whatever. You can have more cars, but if you don't have drivers for those cars, you can't deliver any more pizzas. So, this is a case of perfect complements where there is no substitutability between these inputs. They have to be used in fixed proportions. And lastly, then we have, very similar to the one that we've been using all along. This is the so-called Cobb-Douglas production function. And let me show you, what a Cobb-Douglas function looks like. Let me go back to my whiteboard. I hope. Here we have a Cobb-Douglas production function, which typically is Q is equal to, and what do we have here? A L to the alpha, K to the beta. So these exponents are the parameters in the problem, as is A, and L and K are the variables. So this is my production function. Now, notice that the marginal product of labor is going to be alpha, this is MPL, remember, L to the alpha minus 1, K to the beta. All right, and the marginal product of capital is going to be partial Q with respect to K, and that's going to be beta L to the alpha, K to the beta minus 1. Now, the MRTS, we said, is going to be marginal product of labor over marginal product of capital, which is going to be alpha times L to the alpha minus 1, K to the beta, over beta, L to the alpha, K to the beta minus 1. All right, so this simplifies to, well, alpha minus 1 minus alpha in terms of the L's is equal to L to the minus 1. So I'm going to have alpha over beta, and I'm going to have L to the minus 1, which is 1 over L, and beta, remember I subtract when I divide variable to an exponent. So this would be beta, the exponent, beta minus 1 is just 1. So this would be K to the 1. So that the MRTS for this Cobb-Douglas production function is going to be alpha over beta K to the L. Note that if alpha equals beta, then the MRTS should be on K is just K over L. All right, so in this particular case, if I had Q was equal to, 10 L to the 1/2, K to the 1/2, then the marginal product of labor would be equal to 5 K over L to the 1/2. The marginal product of capital would be 5 times L over K to the 1/2. So the MRTS in this case would be simply, well, it would be 5 times L over K to the 1/2. Whoops, let me make that marginal partial labor, excuse me. K over L to the 1/2 over 5 times L over K to the 1/2. These 5s would cancel, and this thing simplifies out then to K over L because of the 1/2. L to the 1/2, K to the 1/2. So back to my PowerPoint. So this is what is called the Cobb-Douglas production function here, this thing. And most generally speaking, if alpha and beta are 1/2, it's a commonly used example in economics classrooms. Now, let's finish up here. Returns to scale. Returns to scale is a long-run concept that refers to the change in output that's gotten from an equiproportionate change in all inputs. So this has to be a long-run concept. Don't confuse it with diminishing marginal returns. This is when all inputs are variable, and we change all inputs by an equal proportion. We then observe what the proportionate change in output is. So if I increase all my inputs, capital and labor, by 5%, and output increases by 5%, I refer to that as a production technology that exhibits constant returns to scale. If I were to increase all of my inputs, capital and labor, by 5%, and output increased by more than 5%, I would refer to that as production technology exhibiting increasing returns to scale. And lastly, of course, if I were to increase my inputs, all my inputs, by 5%, and output increased by a proportion less than 5%, I would call that diminishing or decreasing returns to scale. All right, so constant returns to scale is when a proportional change in all inputs produces the same proportional change in output. And as you can see here, we go from 50 to 100 to 200, so we keep doubling labor, we keep doubling capital, and output exactly doubles, reading quantities off those isoquants. Increasing returns to scale is when a proportional change in all inputs produces a more than proportional change in output. So once again, we double inputs, and as you can see, output more than doubles. It goes from 100 to 250, 250 to 625. So looking at this isoquant map, I can observe that this production technology exhibits increasing returns to scale. And of course, lastly, decreasing returns to scale. Once again, when I keep doubling my inputs, all my inputs, output less than doubles. So this would be a production technology with an isoquant map that looks like this, that the doubling of my inputs generates less than a doubling of output. So implications here, well, this is an interesting implication. When production exhibits increasing returns to scale, efficiency suggests there should be a single producer because it can produce at lower average cost than could 2 or more producers. But, you know, that's the issue of monopoly here. So we're not going to discuss monopoly in this class, but you probably talked about it in your principles anyway. We're going to, you know, have our review session, and then we'll be talking about production costs in the, you know, next chapter 8. You know, that is to say, we now know the relationship between inputs and outputs. So once we price the inputs, we can get a cost function for our output. All right, so next time we meet, we'll review. I'll try and work some examples for you on both short and long run production.